Hello everyone, welcome to Cambridge Guru. As you know that we are doing complex number, and in the last video we did some questions based on complex number which are given as a set of points in a polar form, right? Next topic that we are going to deal with is complex exponents, and but before that there is a very interesting phenomena that when we multiply any two given numbers in which are written in polar form, so what are the results on the modulus, or what will happen to the argument and the magnitude of the given two numbers. So it says that the polar form quickly leads to an elegant geometrical interpretation of the multiplication of complex numbers. So for if we have been given two complex numbers z1 and z2 which are written in polar form, the argument of complex number 1 is theta 1 and for 2 is theta 2, and magnitude is r1 and r2 respectively. So when we multiply these two numbers, the result will again be a complex number, and that is written by z1 and z2. So what result it will give is that the magnitude are multiplied separately and the arguments are added, right? So as you can see that using the compound angle formula, what we did in this is we have multiplied the two numbers r1 and r2 complex number, right? We can multiply this r1 with r2 separately and then multiply these trigonometric functions cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. Multiplying these two numbers with the two numbers on the bracket, that results give me cos theta 1 cos theta 2 minus sin theta 1 and sin theta 2 plus I times sin theta 1 cos theta 2 plus cos theta 1 sin theta 2, and this is nothing but a formula for cos theta 1 plus cos theta 2, right? So, and similarly for this, we have sin theta 1 plus sin theta 2. So, this is the complex number with modulus r1 and r2, and the argument will be theta 1 plus theta 2. So, we have a very beautiful result here that when we multiply two complex numbers, their magnitudes are multiplied separately and the arguments are added. So we have z1 and z2 magnitude is equal to multiplication of these two magnitudes separately, and the argument of z1 and z2 will be argument of z1 plus argument of z2, and we can do plus minus 2 pi if necessary to give the principal argument or principal value of the argument, right? So it says that to multiply complex numbers in polar form, you just multiply their moduli and add their arguments. Now another interesting phenomena that we can notice here, that if you look at this equation closely, argument of z1 and z2 will be addition of their separate arguments. This law, I can say, or this relation are usually followed by a more, you can say, familiar function, and if you have recognized this, this relation is basically for log functions, right? So if I say that log of a into b, it becomes log of a plus log of b. And the same thing we can do in case of division also. Means if you are if you are dividing two numbers, two complex numbers z1 and z2, so their magnitude will be divided separately, written as z1 by z2 like this, and their argument in that case will be subtracted. So if any function or this argument of z1 divided by z2 becomes argument of z1 minus argument of z2, and in case of multiplication it is argument of z1 plus argument of z2. So these two relation, from these two law, we can say that basically the laws of logarithm can be applied to the argument of two complex number if they are multiplied or divided, right? So this is a very important result that we must remember, right? So quick examples for this are that we have been given two numbers, a complex number, and we need to write down the multiplication of these two. So as I say that you have to multiply these magnitude together. So 6 into 2 will be 12, and their argument will be added because we are multiplying. So argument of complex numbers 1 is pi by 2, and for complex number 2 is pi by 4. So this is 90 plus 45 is basically 135, which we can write as giving the principal value as pi minus pi by 4, which is 3 pi by 4. So this can be written as 12 cos 3 pi by 4 plus I times sine 3 pi by 4. Okay, because arguments are added. For second part, this is the division case. So 6 divided by 2 will be 3, and argument of z1 is 90 degrees pi by 2, and for z2 is 45 degrees. So in this case, arguments will be subtracted because we are dividing. So that becomes pi by 4. So you can write this as cos of pi by 4 plus I times sine of pi by 4. Okay, it's very simple. So next topic is complex exponents, right? And it is a very useful and very interesting phenomena that we are going to experience just now. So imagine you have a complex number z, which is written in, which has a magnitude 1, right? And it is written in polar form like this, cos of theta. So I'm supposing that argument is theta plus I times sine theta. Okay, now what we do is that laws of calculus also applies to complex numbers, right? We can differentiate, we can integrate complex number, and we do differentiate complex numbers. So there is no exception that we cannot apply differentiation or integration or any other calculus rule to complex number. We can apply, right? So what I mean is, if I differentiate this given complex number with respect to theta, so let us see what we observe. So if I differentiate this with theta, so I can write this as dz by d theta is equal to derivative of cos theta is minus sine theta plus derivative of cos theta, sine theta is cos theta. So it becomes I times, as I is a constant, we cannot differentiate just a constant. So it becomes just I. So it is cos theta. Okay. Now what I do is I multiply this equation by the complex number I. So it becomes I times dz by d theta is equal to minus I sine theta. And the moment I apply this I with I, it becomes I square, and I square is minus 1. So this becomes minus of cos theta, right? Multiplying this by I, it becomes I square, which is minus 1. So it is just minus cos theta. Now this is I times dz by d theta. Taking out minus sign outside, it becomes minus of cos theta plus I times sine theta. Right now, if you can see here that this is basically the original complex number, cos theta plus I sine theta. So I can replace this by z. So it becomes I times dz by d theta is equal to minus z. Right now, we can transfer this I to RHS. So we have here dz by d theta is equal to minus z over I. Multiplying and dividing this equation by I, because we cannot keep the complex number in the denominator, because we have to write this in the form of a plus ib or r times cos theta plus I sine theta, right? We do not keep the complex number in the denominator. So multiplying this by I and dividing by I, this gives me minus I times z over minus 1, right? So I have an equation here which is, I can cancel this minus with minus, right? So we have dz by d theta is equal to I times z. Okay, very simple. This original equation can be replaced by, or you can say this is a differential equation of this function, right? Now if I have to solve this equation, let us see what result we get. So transferring or just using the separation of variables, so I can transfer this z in the denominator, so it becomes dz by z is equal to I times d theta. On integrating this, I get ln z is equal to I times theta plus some constant c. This is the solution, general solution. Now in order to find out the value of c, let us see how we can find out this constant. Right now, if I put theta is equal to 0, right? So if theta is 0, that means dz, sorry, not this, dz, the original equation. So if theta is 0, this I times sine 0 becomes 0 and cos 0 becomes 1. So z value will be 1, right? Putting this condition that if theta is 0, that means z is 1. Okay, writing these initial condition in the solution of this, that becomes ln1 is equal to, this is 0 and this is c, and what is the value of log 1? It is always 0. That means this constant is 0, so I can write this value here and say that log of z is equal to just I theta, right? And now finding out the value of z in exponent form, because the topic is complex exponents. So let us see what we get, that since the base here of log is e, so z becomes e raised to power I theta, right? And this is a very important equation, and that is a very remarkable discovery, you can say, as far as complex equations or complex numbers are concerned, right? That your original complex number, first you have a plus ib, right? You can convert this a plus ib in a polar form, writing in terms of r and cos theta plus I sin theta. And again you can write that polar form in the exponent form, which is a more shorter version of the polar form, and it is very easy to deal with. Okay, so this z is just e raised to power I theta, the exponent form of a complex number, where if you have the magnitude of complex number z as r, so you can in general write that z is equal to r e raised to power I theta. This was the case when r was 1, and this is the case when magnitude is r, right? So z is r e raised to power I theta, right? And very interesting relation we can derive from this equation if the magnitude of r is, of magnitude of the complex number is 1, and that is the Euler equation. This Euler equation is considered to be as the most beautiful equation in mathematics. Why it is most beautiful? So let me give you a brief idea about that. So we have this equation, z is equal to r, not r, z is equal to e raised to power I theta, right? And this z is in terms of polar form, having magnitude as 1, can be written as cos theta plus I sin theta. This is the relation that we just derived. Now for the special case, that if theta is equal to pi radians, right? So let us see what is the relation that we get here. So e raised to power I pi is equal to cos pi plus I times sin pi. Cos pi value is -1 and this sin pi is 0. So we have a very important relation, which is e raised to power I pi plus 1 is equal to 0. Transferring this -1 to LHS, you get a very beautiful equation. E raised to power I pi plus 1 is equal to 0, and this is your Euler's equation, right? That was given by mathematician Euler. Now why this is most beautiful? What is the reason? Because as you know that in natural numbers or the whole numbers, or as far as real numbers are concerned, this 1 and 0 have a very special place. Why a special place? Because 0, as you know that it was discovered by Indian mathematicians, and there is a lot of big story about the number 0, right? Sometimes infinite is also related with 0, right? And if you multiply anything with this 0, you will get 0. If you divide this 0 by any number, you get again 0. Similarly, we have a special number which is 1, that if you multiply any number with this 1, you get the same number, not the 0 this time, and if you divide the any number with this one, again you get a same number, right? So 0 and 1 are the special numbers as far as real numbers are concerned. Then we have this irrational number e, right? This is also an irrational number, and it has a special place in real numbers, considering the fact that the rate of change of any function, right, is equal to the function itself, right? That is the definition of a e raised to power x, which is the exponential function, right? That it is changing, its rate of change is equal to the function itself, right? So we have e, if x is 1, you have the special number e, which is irrational. Then comes this pi. This is again a very important number, important irrational number, right? And it has a special place in real numbers also, right? Then we have this I, which is your imaginary number, right? So why this equation is so beautiful, that somehow all these numbers 0, 1, e, pi, right, and this again an imaginary number, they all are combined in a single equation, and they have just become equal to 0, right? So that is why it is more beautiful, and there are various images in internet also you can search of that it is saying that we have these two are talking, right? I is talking to pi, and it is saying that I is saying to pi that become real, sorry, become irrational. I'm sorry. I is saying to pi that become rational. You are an irrational number, you are not logical, right? You are just poof, like kind of a thing. You are irrational, you are illogical, right? So what pi is saying to I that you just become real. Okay, stop talking to me, right? You are imaginary, you just don't exist. Okay, so just become real. Then comes E. What E is saying to these I and pi, that you combine with me like this, we will become 1. Okay, means it's a special case, means you can transfer this plus 1 to RHS. So it is saying that we will become 1. Okay, become 1 means it is saying we will become 1, means this minus sign is read as a dash, right? So there are a lot of t-shirts also that in which these kinds of equation are printed. Okay, so this was a brief idea about Euler's equation, and that's it as far as complex exponents are concerned. And you can do 1 or 2 questions on this that find the value of these, that as you know that these are written in polar form, where argument for complex number 1 is 5, for second is 2, and we know the fact that in this multiplication magnitudes are multiplied, so 4 into 3 is 12, and arguments are added, so 5 plus 2 becomes 7, so e raised to power 7i. In case of division, again magnitudes will be divided, so 6 divided by 3 becomes 2, and arguments will be subtracted, so 9 minus 2 becomes 7 again, e raised to power 7i. Then in second part says that write these complex numbers in polar form, so you can write this as 12 cos 7 plus I times sine 7. Remember, in these polar form, this theta is always written in terms of in real numbers or in radians, right? Do not consider this 7 degrees, it is 7 radians. Okay, similarly it is 2 cos 7 plus I times sine 7. Okay, so that's all for the introduction of complex exponent. See you in the next video, we will solve some questions. Okay, thank you, bye.